I'm Erica Zavaleta, and this is Ecosystems of California. And I'm at Seacliff State Beach on the northern end of Monterey Bay. Behind me you can see the curve of the bay as it goes first east, then south, and curves back around far behind me, but that's mostly obscured by the fog. So California's climate is really diverse for a bunch of reasons. It's north to south length, which is 800 miles or about 1,300 kilometers. It's really strong gradient from the ocean going inland, and it's many and varied mountain ranges and elevational diversity. So today we're going to travel a transect. We're going to travel from west to east across California, starting at the ocean and ending in the desert, to have a look at some of that climate diversity. We're starting here at the ocean early on a summer morning. Temperature is about 59 degrees, the winds are calm. The temperature is incredibly stable at the California coast, and that has to do with the incredible thermal mass of the Pacific Ocean. So in the summer, the Pacific is cooling the air. In the winter, the Pacific is keeping it relatively warm, and the temperature only swings 5 to 10 degrees Celsius on average between summer and winter here. Another thing you can see behind me is this marine stratus layer, or high fog. And this is typical on the California coast, especially in the summer. And the way that advective summer fog works is kind of like this. So the Pacific Ocean here in California is marked by strong upwelling most of the year. And what that means is that longshore winds push the surface waters away from the coast, and that pulls up cold water from down deep. So because that water is upwelling right at the coast, it turns out there's a temperature gradient. As you come into the coast from out at the ocean, it actually gets colder. And so in the morning, when the sun comes up over California and air starts to warm and to rise inland, it pulls moist air over the surface of the ocean in the marine layer. That moist air encounters these colder waters near the shore, and it gets cooled by that water surface, reaches its dew point, and some of that water vapor condenses out as fog. It happens up high when the marine layer is thick, when the temperature inversion over the ocean that's driven by the cold surface is deep. And so today, that marine stratus layer, that moisture is coming out towards the top of the inversion. That fog can get drawn inland, and so on some summer days when it's really hot in the interior, it'll enter through the Salinas Valley and the San Francisco Bay and stretch all the way to the Central Valley. So let's leave the ocean behind and head east. So we're 25 miles from the coast now, and you can see behind me that we're nearing the end of this fog layer, this marine stratus layer. So the coast ranges can block that stratus layer from entering inland, but where we are now near Hollister, California, there are some valleys, and so as that warm air behind us is rising, it's pulling air in from the ocean inland and bringing that fog in many miles from the coast. As we move that way, we're going to be moving into an area of much, much higher temperatures and drier air that's more typical of California in the summer. So why doesn't it ever rain in California in the summer anyway? The main reason is that there's something called the North Pacific High. It's a big atmospheric system, and it's always out there, but it sits in different places at different times of the year. And in the summer, it just parks itself over California. It's a high-pressure system, and it basically just rebuffs any storm system that comes into the area, kind of bounces off of that high pressure and gets held off of the coast. And it sits there until sometime in September, October maybe, and then it'll move out offshore, and the storms can come down and in from Alaska and other places in the North Pacific. So that system of that high moving up over California is really stable. It's been doing that for at least a few thousand years, and as far as we know, it's going to keep doing it into the long future. And until it stops doing that, we'll continue to have these totally dry, rainless summers over much of the state. We're now at San Luis Reservoir on the edge of the Central Valley to the east, and just over Pacheco Pass out of the most interior ridges of the Coast Range to the west. And we've come out of the fog. It's pretty windy up here. The wind is funneling through Pacheco Pass from the ocean. And because the air has been forced up the mountains, it's left the fog behind. So San Luis Reservoir is part of the State Water Project. It was built in the mid-1960s and first filled in 1969. It's a storage facility. So water is pumped here from the Sacramento-San Joaquin Delta, and then it's stored here and conveyed from here to agricultural users throughout this region for irrigation. It's an interesting part of this incredible infrastructure of water delivery that marks California, partly because it has this summer drought seasonality. And one of the things you can see behind me is that the reservoir is really low. So there's been quite a bit of drought lately, and the long-term trend in California has been of declining precipitation. And San Luis Reservoir dropped to as low as 17% of its capacity. So climate change is not the main thing that we're talking about today and looking at today, but it is this backdrop against which we look at the climate of California and its long-term trends. The other thing you can see behind me is that the hills now are really dry. It's a lot drier here than where we left the coast this morning. And that's because now we've come over a few ridges of the Coast Range. So we're in the rain shadow of the Coast Range here. Precipitation here is about half of what it was in Hollister at our last stop, which is in turn about half of what it is at the coast. And what's happening is that those same moist air masses that create the fog at the coast in the winter here are moving in from the ocean, and when they hit the mountains, they begin to rise. As they rise, they cool adiabatically. Adiabatically means that they're not giving off heat, they're just losing energy because they're expanding from the decrease in pressure. So as those air masses rise and cool, they can reach their dew point so that the moisture, the water vapor in that air condenses, and it can form mountain clouds and rainfall. That's one of the reasons why as you go up in elevation on the windward side of mountains like the Coast Range and the Santa Cruz Mountains, you can get precipitation levels that are much higher than they are down closer to sea level. So the air masses come up the mountains, they cool, they drop moisture, they come over the backside of the mountains, and then they begin to sink. And they've had all the moisture wrung out of them, or a lot of the moisture wrung out of them from that rise. They drop. As they're dropping, they warm now because they're increasing in pressure, and so they hold on more tightly to their water and they're less likely to drop it as precipitation. So that's happened once over the Coast Ridge. It's happened again over the interior ridge of the Coast Range, and now we're back on the backside, and these sinking warm air masses are hanging onto their water and much less likely to rain. And we'll see the most dramatic rain shadow in California at the eastern end of the state when we cross over the Sierras into the Great Basin Desert, which itself marks the rain shadow of that big mountain range. So we started at the Pacific. We stopped near Hollister, California, and over the interior Coast Range at San Luis Reservoir. We've crossed the Great Valley now, and we're in the foothills of the Sierra Nevada. And behind me you can see them rising up with some oak woodland scattered into these grasslands, a little bit of savanna. So as we climb the Sierras, we're going to climb out of what's right now a pretty hot, dry place. Temperatures in the high 80s. It's midday in August. And as we rise, we'll be rising with that air that's coming up out of the valley and adiabatically cooling, so the temperature will drop as we go up. For the same reasons that it gets cool as we go up, the precipitation levels are going to go up as we climb into the Sierras. So air masses from the Pacific, by the time they reach the Sierras, have lost some of their moisture in the Coast Range mountains. But they get to the Sierras still laden with a fair bit of moisture, and of course the Sierras are a lot higher. Now we're going up to over 4,000 meters in some places. So as that air rises up the Sierras, it drops a lot of moisture. And so that mountain precipitation, which falls mainly in the form of snow because we're in that Mediterranean climate system, can accumulate to levels on average of about 10 meters a year at Donner Summit. A ton of snowpack, with some of the sites receiving higher levels than anywhere else in the continental US every winter. So we're going to head up into the mountains now. So now we're nearing the top of Tioga Pass, near the top of the Sierras at about 3,000 meters in elevation. And even though we're at the top of the Sierras, we're still in a region heavily influenced by the Pacific Ocean. We started the Pacific 300 kilometers ago and have come over the Coast Range, across the Central Valley, up into the foothills and up the Sierra. Behind us are the mid-elevations of the western slope of the Sierras, where most of the precipitation in the winter typically gets wrung out of the air as it's rising up. And at the top here, at this point, the main features of the climate have to do with cold. Most of the precipitation up this high is falling as snow because there isn't summer precipitation for the most part. And so organisms up here have to deal with a real mismatch between the growing season and the timing of water availability. The temperature here is much colder. Even now in August, it's probably 60 degrees out right now, dropping into the 50s as the sun is setting, but also because we're above 3,000 meters. And then finally, the temperature variability, the range up here is really high. In the middle of the day here in the summer, we're hitting pretty hot temperatures, and at night, even in the summer, temperatures can drop down to freezing. The annual variability in temperature at this site is also totally different from at the ocean. Instead of a fluctuation of on the order of 10 degrees, here the fluctuation and the difference between mean temperatures in the summer and the winter are 40 or more degrees. So now that we've crested the Sierras and come down their eastern side, we're about 220 miles from the ocean, or 350 kilometers, almost as far from the ocean as you can get and still be in California. And we've entered the enormous rain shadow of the Sierra Nevada, which extends not only across eastern California, but also across most of Nevada and into Utah. That enormous area of arid lands that's shadowed from the ocean by the Sierra Nevada is the Great Basin, which you can see the beginning of behind me. So the other thing that's changed dramatically as we've gone from the coast to here is that at the coast, annual temperature fluctuations are on the order of 5 to 10 degrees Celsius, whereas out here in the desert, they're much, much larger, 35 to 40 degrees Celsius on average between the July maximum and the January minimum mean temperatures. And so you can have temperatures well below freezing here in the winter and well above 40 degrees Celsius or 100 Fahrenheit in the summer. Ocean, altitude, mountains, and wind shape California's climate, and we haven't even looked at winter or about the variation that stretches from the north to the south.